Welcome, everybody, to our February novice meeting of the Houston Astronomical Society. My name is Chris Morissette, and I'm the novice chair. And we have a great guest speaker tonight, Rich Wilburn. Rich has spoken to the club, to the novice group before, and the presentations have been wonderful. So tonight, and I'm getting to my notes here, so bear with me a little bit. So Rich will be presenting a topic entitled "Our Universe: The Big Picture." And I'm going to read a little bit from Rich's excerpt that was posted on the Astronomical Society website. Exactly what is the structure of the solar system, the galaxy, the universe? We've all been there trying to make sense of the terminology and the immense scale of it all. In this presentation, we'll start with an updated view of the solar system and zoom out to the very edge. We'll see where life may exist in our solar system and around other stars. We'll catalog the components of galaxies, and we'll see how galaxies string together in vast sheets across incredible distances. So that sounds like a very ambitious topic. A little bit about Rich. Rich is a retired IT project manager with a lifelong interest in space and astronomy. As a teenager, he started an astronomy club in his hometown of Jackson, Mississippi, and actually ground a mirror for his own 10-inch reflector telescope. Um, Rich studied astronomy at the University of Texas in Austin, and he spent 2 summers working at the McDonald Observatory. And as an HAS club member since the 1980s, his interests have evolved from visual observing to astrophotography. And one thing I will also say here uh, is that the not only is he migrated to astrophotography, Rich is an outstanding wildlife photographer as well. Taught me a few tricks here back, so that was
I appreciate that.
very much appreciated. Okay, so with that, I'm going to stop sharing my screen, and I need to make you a co-host. So let me do that. And let me see where that is. Make you a co-host. And with that, Rich, you should be able to share your screen. As Rich is presenting, if you would stay on mute and put your questions in the chat. And then when we get done with the presentation, we'll go back and go through the chat and get the questions answered. So with that, Rich, take it away.
Okay, let me just get the share going here. Just 1 second. It's always tough to get started. All righty, here we go. All right, so you know what I notice a lot of times our astronomy presentations get very, very narrow. And I wanted to do a talk today that just gives a really big picture because I've got a lot of friends who are relatively new to astronomy, and it seems like there's a lot of things that are missing and a lot of pieces that are just kind of go unspoken. So that's what we're going to talk about tonight. We're going to talk about the structure of the universe, and we're going to start with the solar system, and we're going to move out from there and give the big, broad picture view of basically astronomy 101. So the first thing we're going to do is take a look at the solar system. And what I love about this diagram here is it shows the planets and the sun to scale. So if you just take a second to look at it, you'll see that the Earth is very small. The sun is very big and the outer planets are gigantic. And it's kind of refreshing just to see everything to scale. But now the distances, out between the planets is not to scale. This is just the diameters of the planets. So when we talk about the solar system, the place to really start is with the sun. And the cool thing about the sun is just look at the size of it there compared to the Earth. Now I've got some notes here. You may hear me turning the pages because I've got a lot of numbers I want to keep up with. The sun is a giant rotating ball of hot plasma. It's mostly hydrogen, which is the most abundant element in the universe. And every second, the sun fuses 600 billion tons of hydrogen into 596 billion tons of helium. And that missing 4 billion tons, well, that's converted directly to energy by Einstein's equation E equal mc squared. And at that rate, the sun can continue to shine for 5 billion years. It's just amazing, an amazing process. And this is that incredible source of energy you hear people talking about trying to do a nuclear uh, fusion. Sorry, not fission, fusion. So it is an amazing thing. The sun is also 8 light minutes away. So when we see the sun, we're seeing it, well, like 8 minutes ago. If we start with the inner planets, Mercury and Venus, Mercury is just a scalding hot ball of rock. It's tidally locked, so one side always faces the sun. That side is up to 800 degrees Fahrenheit. The side that faces away is minus 290 degrees Fahrenheit. Venus, on the other hand, isn't much better. Venus is a runaway greenhouse planet about the size of the Earth. It has a atmosphere made mostly of carbon dioxide, 50 times more dense than the Earth. And amazingly enough, we have pictures of the surface thanks to the Soviet Union space program from back in 1981. And these things actually survived on the surface for minutes, but long enough to send back pictures of what Venus looks like. Okay, when we get out to where the Earth is, the interesting topic there, I think one that everybody loves are meteors. We've got about 50 tons of meteor material that hits the Earth every day. And every year, there's, of course, a bunch of little meteor showers, but you'll notice that there's two that are particularly good. There's one in August, the Perseids. There's one in December, the Geminids, and those are really worth going out to the dark sky site to see. That can be a very, very pleasant evening. But when you go, you need to check the moon phase because the moon will produce natural light pollution, and it doesn't help that it's natural; it's still light pollution. It'll outshine most of those dim meteors. But now here's the thing: is even though most of these meteors are tiny little bits of debris that burn up in the atmosphere, make us where we can see them, they're like the size of a grain of sand. Every now and then you get a big one, and this is a video. I'm going to mispronounce it. The Chelyabinsk meteor that entered over Russia in 2013. It was about 60 feet across. It exploded high in the atmosphere. It was going around 42,000 miles an hour, and it injured people. 1,491 people were indirectly injured, and this is horrendous. They saw this flash. For a moment, it was brighter than the sun, so you'd run to the window to look out, and then the shock wave hit and would shatter the window right in their face. So here's a little tip for you. If you see a meteor passing overhead, don't run to the window. There were over 7,000 buildings damaged as well. So a lot of people don't realize that there is stuff up there that can hit the Earth and has hit the Earth in the past. If we look at a map of the existing craters across the Earth, there are craters. There's about 200 on the Earth of varying sizes, and there's 3 in Texas. Now, these haven't happened recently. These are like 10,000 to 100,000 years ago. But every now and then, something hits the Earth that's a pretty reasonable size meteor or a small asteroid. Now, you can just look at the moon. Since it doesn't have an atmosphere, you can see it's just pockmarked with craters. For a while, we didn't know if those craters were created by volcanoes or by meteors, but we know now they're mostly meteors. And it's a testimony to the early days of the solar system. It was just a demolition derby where there's a lot of debris flying around out there and a lot of impacts. Here's an image of the moon and the Earth to scale. If you have a standard 12-inch globe of the Earth like they have in classrooms, then the moon is about the size of a tennis ball. That's helpful to know. But what a lot of people don't know is the distance. The actual accurate distance between the Earth and the moon is, well, it's illustrated here. If you use that same 12-inch globe for the Earth, then the moon would be 30 feet away. It's 30 Earth diameters away from the Earth. And it's enough space that you could put all the planets and the rest of the solar system in the gap between the Earth and the Moon. So how about that? On to Mars. Mars is the most Earth-like planet. Um, it has a 24-hour, 39-minute day. The temperature range at the equator can go from 68 degrees, noon on a scalding hot day, down to minus 100 degrees at night. It has polar caps, and if you guys have never seen Mars through a telescope before, then you're in for a treat because the polar caps really make it look very much like a planet you'd recognize. It looks a lot like maybe the Earth at a distance. It has two small moons that are probably captured by asteroids. But what I want to call your attention to on this side is look how far we've come in understanding Mars, going from Percival Lowell's drawing in 1905. This was the best anybody ever saw Mars, was right there, up to a panorama from the Mars Curiosity rover. We're looking at Mars at point blank range. And the cool thing too is that we have found the potential biosignatures of life. So, we keep looking for signs of life. We found signs of minerals that existed in the presence of water, possible biosignatures of life on Mars. And of course, the big holy grail is to find definitive evidence of life on Mars. If we move out to the asteroid belt, here's a sample of some of the asteroids. They're just small rocky bodies. Most of them are too small to assume a spherical shape. If you have enough gravity, gravity will pull everything together. So you see Ceres is just right at that minimum size to make itself round. Here are some of our other asteroids to scale next to the Earth, and you can see how irregular they are. Now, one of the things about the asteroid belt people get wrong is they think we've seen so many movies where the hero's in a spaceship and he's flying through the asteroid belt and it looks like he's trying to cross I-10, I-10 West with the 30 lanes of traffic at 5 o'clock, on a Saturday. It's not like that. The average distance between asteroids is 600,000 miles. So that's just a movie contrivance and it's fun to watch, but it's not reality. But here's a kind of a cool image. When I got started interested in astronomy, asteroids are just points of light. And today they're actual 3D objects we've been to and visited. And not only that, we brought back samples. So how's this for seeing an asteroid up close? This is from the OSIRIS-REx mission, a sample of asteroid Bennu. And they're finding in these samples organic and inorganic molecules, including amino acids, which are the building blocks of protein. And proteins are the building blocks of us and other forms of life. So that's really cool. A lot of people, when we talk about comets, they're so deceptive. If you look at a beautiful picture like this, it looks like a 4th of July firework where it's just shooting across the sky, but they're not. They just look like that. Comets are icy bodies, rocks and ice. They get close to the sun. The water starts to evaporate and produces a trail behind it. They're cool to look at up close. And if you ever get to see a bright one, don't miss a chance. The first one I ever saw was stunningly bright. It was Comet Bennett, and it was about the size, the tail was about as long as your finger at arm's length, and it was just a remarkable thing. And that kind of spoiled me for any other comet since then. Okay, moving out next, we come to Jupiter. And here's the thing, all the planets we've talked about so far are rocky bodies, but Jupiter is not. Jupiter and the rest of the gas giant planets are just that. They're gas giants. They don't have a sudden solid surface like the Earth does. If you could take a stick and poke Jupiter, it would kind of mush into it. I mean, there is it gets harder and denser at the core, but it doesn't have a solid transition to the surface like we do here on the Earth. But the cool thing about Jupiter is it rotates in 9.9 hours. And so if you're looking through a telescope over the course of an evening, you can definitely see it rotate, especially if that means the red spot's moving into view or moving off the planet. It has a total of 95 moons, which you might think is a lot until we get to Saturn. But the coolest moons are the 4 big bright moons that were discovered by Galileo in 1610, Io, Europa, Ganymede, and Callisto. Io, it's up here in the top right. I don't know if you can see me pointing. It's the most volcanic object in the solar system. It gets squeezed by Jupiter's gravity because its orbit's not perfect, and sometimes it comes closer, sometimes farther away, and that squeezes the planet, the moon, just like all of these get squeezed. And that squeezing heats up the core and causes these volcanoes to go off. Europa is the number one candidate in the Jovian system for life. And there's actually a spacecraft on the way there right now called the Europa Clipper. It's going to get to Jupiter in 2030. And its mission is to look for evidence of locations on the surface or that could support life. Europa and the other moons of Jupiter are covered in a layer of ice, and we think that underneath that ice layer is water. And wherever there's water, at least on Earth, there's life. And that water may be warmed by hydrothermal vents like we have on Earth, and those hydrothermal vents are just loaded with life. So the first step is to try to find locations on the surface to go and look, and hopefully at some point a Europa lander will go in and burrow through the ice, and maybe in our lifetime or the lifetimes of our kids and grandkids, we'll actually have the discovery of life in the solar system. So there's Jupiter. Saturn, a really cool planet. If you're holding your breath on how many moons? 274 at last count. Too many to mention, except for these three. Titan, which is incredible. It has an atmosphere. It is really a large moon. We'll talk about that more in just a minute. It's also the largest moon of Saturn. Mimas is kind of cool because anybody that loves Star Wars will look at that and go, "Oh, there's the Death Star," and whatever hit Mimas there at the 3 o'clock position really left a hell of a crater. And then Enceladus is another potential location for life in the solar system. Enceladus also has a icy layer, believed to have an ocean of water underneath it. And some people have said that really the Europa Clipper should have been the Enceladus Clipper. We should have gone there for our first attempt to look for life in the solar system. So we really have a lot of cool opportunities in these outer planets and these moons. If you look at Enceladus again, this is really cool. In 2009, the Cassini spacecraft photographed water geysers coming out from Enceladus. So something is, of course, we definitely have liquid water, and then the heat underneath is causing this water to be ejected just up into space. But what I like is the title. The Water Geysers of Enceladus sounds like a cheap science fiction story paperback from the 50s, and yet it's a reality today. But I tell you what's really cool is if we look at Titan, I think it was a Cassini spacecraft that launched a lander that landed on Titan. And what we see here is it looks kind of blurry, and it's blurry because we're looking through an atmosphere that's 50 times denser than Earth's atmosphere. Titan is bitterly cold, like 300 degrees below zero. It has oceans of liquid methane. And the basic composition of Titan, they think, is somewhat like the early Earth. But my favorite fact about Titan is that because the atmosphere is so dense, an astronaut on the surface would not have to have a pressure suit. All right, now you'd still have to have the suit to keep you warm from turning into a human icicle. But with that dense atmosphere and the low gravity, some people think that an astronaut could jump and you could paddle in the air and you could actually float, maybe even fly on Titan if you could just paddle yourself up like that. So can you imagine some astro tourists in the 22nd century going up to Titan to just go fly, the human dream? All right, and we get to the outer solar system, Uranus and Neptune. The cool thing about these planets is if you get a chance to see them through a telescope. I think I saw Mike McCurdy online. He brought his Dobsonian out one time, and when we looked at Uranus and Neptune, they actually look like these colors. They're not that big, they're smaller, but they're clearly disk, and these are clearly the colors. If you look at Uranus, you'll see that its axis is tipped over at 98 degrees. Remember how I said the early solar system was a shooting gallery? Well, there's a lot of collisions that went on early in the history of the solar system, and it looks like Uranus really got knocked over. Now moving on to Pluto. Pluto, not a planet anymore because basically the planets have to clear their orbit, and Pluto hasn't quite done that. But it's turned into a much more interesting planet than people realized, or excuse me, a planet, almost planet. It has 5 moons, and it has a second moon, Charon, that is so close in size it's practically a double planet. The other ones, Nix, Hydra, Styx, and Kerberos. I mean, what a cool combination of planets and excuse me, of moons. So Pluto's definitely interesting, but Pluto is actually, rather than being a true planet like what we're used to, it's actually a member of a new set of objects in the solar system called Kuiper Belt objects. So out, really starting with the orbit of Pluto and farther out, there are these Kuiper Belt objects, also known as trans-Neptunian objects. And I mean, a lot of these names are new to people who've been in astronomy for a while, but we keep finding these pretty large objects out at the outer edge of the solar system. And of course, the smaller ones that are icy bodies, they think they're there by the thousands. The Kuiper Belt looks kind of like this. It's bigger, much larger than the asteroid belt. So if you really want to do a science fiction show and have your hero flying through a dangerous, congested part of space, make them fly through the Kuiper Belt rather than the asteroid belt. And here in this illustration, you can see how Pluto dips out and then comes back in. So it's really on kind of a wonky orbit, but it's clearly more of a Kuiper Belt object than it is a true planet. Okay, beyond the Kuiper Belt, we think that there's a giant cloud of material left over from the formation of the solar system called the Oort cloud. And a lot of long period comets have been observed coming from this region. The way I think about the Oort cloud is, do you know how when they build a house and there's all this debris left over after they finish it, they don't pick their own stuff up. There's nails and, 2x4s and stuff out there in the yard. Well, here's the leftovers from the early formation of the solar system that's just going to float out there and never going to get picked up. So we've got the Oort cloud. Okay, now comes the time when we got to talk about the speed of light. Speed of light and how far light travels in a year, a light year, is such a unit of measure in astronomy, and I've been racking my brains how to visualize it. And the best I can think is it's like this. Most of us on the call here have been to Dallas, have driven that route before. So if you drive to Dallas from Houston and back 390 times in 1 second, that's the speed of light. So it's kind of hard to imagine, but it's a way to get a handle on it. And the other thing, it's real tempting to think, well, okay, that's fast, but couldn't you go any faster? And the answer is no, because the way the universe works is as we get closer to the speed of light, weird things happen. Masses get heavier, time slows down. There really is a fundamental limit, fundamental speed limit in the universe, and that's the speed of light. But that's pretty damn fast. But if you'll hold that thought in mind when we start talking about some of these other distances, then it'll help give maybe a little bit of insight into just kind of incredible distances we're talking about in astronomy. Okay, so here's our immediate stellar neighborhood. I just love these diagrams because you can really make sense out of some stars that we can see tonight. Sirius right there in the let's see, let me point it out right there if you guys can see that on the pointer. Right there at 8.6 light years. Vega, 25 light years. If you know anybody that's 25 years old, point Vega out to them sometime and tell them that, your light you're seeing now is left Vega the year you were born. So when we look out in space, we're also looking back in time. Just like the sun is 8 light minutes away and Vega is 25 light years away, we're looking back in time. So this is our immediate solar neighborhood. If we move out from there, the big picture is our galaxy. So all of these stars make up a giant flat spiral disk called the Milky Way. It's amazing that it's been mapped. I don't know if you guys can see the pointer. Here's the sun down at the bottom center of the diagram. And at the very bottom left, you'll see another illustration how it's a disk and with a bulge at the center. This is the big picture of our Milky Way. We're talking about 100 to 400 billion stars. And we're finding that most of these stars have planets. So, more than 400 billion planets, probably a trillion or more. And 100,000 light years across, about 1,000 light years thick. So that's our big neighborhood. What does it look like from the ground? It looks like this. I volunteer at the George Observatory, and I'm sad and surprised when I talk to visitors and I find out very few people have ever seen the Milky Way with their eye. And if anybody on the call is in that category, I urge you to go out to the dark sky site sometime. Summer is the best, and see the Milky Way with your eye. And to really, really see it at its best, go out to someplace like Big Bend, take a cruise, get way, way away from city lights. It is absolutely amazing. It just to your eye, it looks like a smear. It looks like thin milk that's been spilt on dark tile. One of the things that happened at McDonald Observatory when I was a student, they told a story about a couple of astronomers who were going in for their midnight meal to the cafeteria, and they passed the dome from another guy that was working, and it was closed up. The shutters were shut, the lights were off. All locked up. So they get into the cafeteria area, and they see the guy's lounging on the couch. He's been there for a while, and they say, "Hey, are you done? I'll finish for the night." He said, "No, man. There's clouds coming up there in the east." And they looked at each other and told him, "No, man, those aren't clouds. That's the Milky Way rising." This guy, who was a PhD or a postdoc or getting his PhD, had never seen the full glory of the Milky Way before and didn't recognize it when he did. And it is just a cosmic, wonderful bucket list thing that everybody needs to get to see at least once in your life. I got to see it once a quarter or it makes me crazy. If you get a telescope and you zoom in on the Milky Way like Galileo did, here's what you see. It's not a smear of light, it's all stars. And here we are looking across such a vast expanse of distance. These stars are separated by tens or hundreds of light years. And so the distance from one corner to the next is just unfathomable. Remember, we're talking 390 round trips to Dallas in 1 second. And at that speed, you're still tens to hundreds of light years away. And when they turn around and look back at us, we could be any one of these little blips of light. Okay, real quick, when talking about stars fall into different categories. Astronomers have categorized them based on their spectra. Spectra is when we take the light from a star and we spread it out into its component colors. And when we do, we get kind of a fingerprint of what the star looks like and what it's made of. And based on that fingerprint, we can tell how much or if it has what chemicals in it. Here you can see iron, hydrogen, helium, oxygen, sulfur, all kinds of different elements that show themselves in the spectra. And the categories of stars are basically what you see here: O, B, A, F, G, K, and M. In the background image here, you see some different sizes. So we've got tiny red dwarf stars, and then we've got, of course, the sun in the middle, and then blue-white supergiants, red giants. They go all the way up to gigantic sizes. It is amazing. All righty. If we go and we think about the life cycle of stars, just like everything, stars are born and they mature and then they die. There's two paths. Stars start out in a stellar cloud, a cloud of gas. And if we take this top route, they turn into an average star, which burns for billions of years, eventually balloons out into a red giant. That outer atmosphere gets puffed off into what's called a planetary nebula. And what leaves behind, what's left of the star, is called a white dwarf. On the other hand, maybe more interesting, the more massive stars, they live a shorter life. You give them all that extra material and they blow through it. They go and turn into a red supergiant. They will then eventually go supernova. And then the remnant of the supernova will be either a neutron star, which is even smaller and more dense than a white dwarf, or it just collapses completely into a black hole. But basically, the weight of the star is so much, the weight of the material is so much that nothing can oppose the collapse and it just shrinks down and shrinks down. And as far as the physics goes, it goes down to the size of zero. And no one knows exactly what the physics are at the core of a black hole. But that's what that looks like. Stellar lifespans go from 2 million years to a blue giant, up to 11 trillion years for a red dwarf. And then the masses of stars go from like zero point 0.8 of a solar mass for a dwarf all the way up to 150 solar masses. Okay, one of the cool things about stars when they go supernova is we can see them. In the bottom left here, here's a galaxy M101, and some of you guys may remember we had a supernova there. I don't know, was it 4 or 5 years ago? And you can see this star wasn't there, previously, but it when it exploded, it is so bright that it is just about as bright as the galaxy. That lasts for a week or two, and then it'll fade away. After these stars explode, they leave their stellar guts out in space, and they make for some wonderful astrophotography. And my astronomy buddy, club member Steve Brown, has taken this gorgeous picture of the Veil Nebula, and I just think it's fantastic. And this is just what's left of this star after it exploded. When we talk about the little more mundane planetary nebulas, for the lower mass stars, they're called planetary nebulas because they look a lot like planets. And if you look at this image in the bottom right, it's small and round. It has kind of sharp edges. Not all of them have that donut hole at the center. So it's easy to mistake it for a planet. And then when you look at it with a big telescope like this image here, it's really beautiful. And there are whole sets of planetary nebula that are really cool to see visually or to photograph. They're a treat to look at in the sky. And what's going on in the Milky Way? We are still forming new stars. This is part of the Eagle Nebula. And here we discovered these objects called evaporating gaseous globules, EGG, eggs. So we have eggs in the Eagle Nebula, these little buds that are coming off here. They're still light years long, but interstellar dust is dense enough that they're starting to collapse under their own weight. And once they get dense enough and there's enough pressure at the core to fuse that hydrogen together into helium, then they'll ignite and become new stars. We also see new solar systems forming in the Milky Way. This is a remarkable image from just a couple of years ago by the James Webb Space Telescope of a solar system forming. And you can see there's a disk here of debris. This is where that demolition derby is going on, where all the debris is going to eventually coalesce into planets and moons. What doesn't fit in nicely is going to eventually get kicked out, and eventually we'll wind up with a nice regular set of planets orbiting this new star. This is maybe the coolest slide in the whole deck. The idea that there is a website called Potentially Habitable Worlds just blows me away. It was 1995 that the first exoplanet was discovered. And in the years since, we are now up to 6,087 planets that have been discovered outside of the Earth, around other stars. And of those, there's about 70 that they believe are potentially habitable. And the criteria for that is the size. If it's too big, it would be more like a Jupiter, which doesn't look habitable. If it's too small, it can't hold its atmosphere. It also has to be the right distance from its star so that basically you can have liquid water on the surface. So just in the time since 1995, we found 70 of these objects, plus all the other extrasolar planets that have been found just in that time. It's just amazing. Okay, what else do we have in the Milky Way? We have a Mission Nebula, also called an H2 region. H2 means that it's basically hydrogen gas that's been excited from the radiation from nearby stars, and it's glowing all by itself. So this is the famous North American nebula here. It looks like North America. I hope you guys can see my pointer. To the right, there's the Pelican Nebula, which you really have to strain. It looks kind of like a pelican. But right in between, there's a little rat face, and I call that the Possum Nebula. I'll fight you on this one. To me, it looks like a possum looking out from between North America and the Pelican. Okay, the cool thing about emission nebulae, they're not just visible in our galaxy. When we look at other galaxies, we can still see them. So here's a galaxy that shows all of these red spots here, and every single one is an emission nebula, clouds of gas that are glowing on their own in another galaxy. In addition to emission nebula, we have dark nebula. So nebula doesn't have to glow. It can just be blocking the view from behind it. So there's basically a couple of categories. One are large molecular clouds that can be dozens or even hundreds of light years across. So that would be like this one in the bottom right, or the famous Horsehead Nebula. Or you can have smaller objects that are called Bok globules that are just smaller pieces of nebula that are condensing under their own gravity, may very well form stars in the future. Both of these categories of nebula, they're dark just because they're not glowing and they're blocking the light from the stars behind them. A quick story about the Bok globules. When I was working at McDonald Observatory, one summer I went walking up to the cafeteria for lunch. And when I did, I saw this car that had not been there before with California tags, and the license tag said BOK, Bach. And it was Bart Bach who had named these, and he was at the observatory for that week. And I had a chance to have lunch and dinner with him a few times and ask him about Bach globules. So that was kind of cool. Okay, when we talk about dark nebula, let's also remember that if we look up at the Milky Way and we see gaps in the Milky Way, those are not missing stars. That's dark nebula. That's a dust and gas that is not glowing, that is just blocking the view from behind. So if you take a photo of the Milky Way, it becomes much, much more clear. But a lot of times, in the summertime, it looks like the Milky Way, it's almost split, but that's not two pieces of Milky Way. That's just stuff in between us, blocking the view from behind. Okay, another category, reflection nebula, which kind of says it all. It's nebula that's just glowing, picking up the light from a nearby star. And I'm real proud of this picture. This is one of my successful astrophotos. I think this is a 12-hour exposure. About the only thing I did on that astrophotography trip, but I'm real happy with how it turned out. Okay, back to talking about stars. About half of the stars in the sky are not single, they're double. And double stars can either be apparent doubles, where they look like they're lined up, but they're not. They just have to be in the same direction. A great example of that is Alberio in the constellation Cygnus, which is beautiful, beautiful combination of star colors, but they're not associated with each other gravitationally. But then you have some other stars, and like here's 70 Ophiuchi, that actually does orbit. We have stars orbiting each other, and over the course of centuries, astronomers have actually tracked it out. We even have a triple and quadruple star systems and higher. So stars can occur in multiple systems. And these are all gravitationally bound, of course. They don't always form by themselves either. Stars can form in clusters. This is probably more common. So two of the most common and two of the most beautiful star clusters in the sky. One of the Pleiades, which you can see tonight, the Seven Sisters. They're ancient. They're mentioned in the Bible and in the Odyssey, and they've been known as long as there have been humans on the Earth. And then maybe the slightly less well known, the double cluster in Perseus. So star clusters, stars that probably formed together out of a common molecular cloud, are gravitationally bound, but the longer they live, eventually their motion through the galaxy can spread them apart, and then they kind of like leave home. As opposed to open clusters, we have globular clusters, which are a glob, basically a big sphere of stars. And these are really beautiful to see through a telescope. I hope you guys get a chance to see one visually. They are not in the disk of the Milky Way like the star clusters are, the open clusters. They're in a halo around the Milky Way. And here's an image of M13 that I took a couple of years ago. And nearby, there's a galaxy way out there in the distance. Okay, at the center of the Milky Way, our own black hole, Sagittarius A star. Really the coolest thing in the Milky Way, and something that was not really accepted for sure. We didn't know for sure these guys existed until not too many years ago. Sagittarius A star, 4.3 million solar masses at the center of the Milky Way. Its its black hole limit of no escape is about the size of the orbit of Mercury. Beyond that, there is material orbiting around it, and it's incredible. Now, a lot of thinking is that most large galaxies have black holes at the center. And the question is, well, did the black holes form first and then that galaxy formed around it? Or did the galaxy form and then the black hole developed at the core? Black holes and with the exotic physics that goes on at the center are an area of just super red hot research right now. And here is a video. Can you believe this? A video of stars at the core of our Milky Way orbiting the black hole. You can't see the black hole because it's black. It's not active. If there was material orbiting the black hole that was starting to interact with each other and generate X-rays or other radiation, we could see that, but fortunately that's not going on. But what you can see are these objects orbiting a mysterious empty object, which is our Sagittarius A star black hole. Also in the Milky Way, it's believed that there are stellar mass black holes, just a couple times the mass of the sun, and they may number from 100 million to a billion. So black holes are everywhere, and I've heard a question about whether or not it's possible black holes might be accounting for the missing mass, the dark matter that's been discovered in the universe. Nobody knows yet. I don't think stellar mass black holes like this have been found for sure yet in the Milky Way, but all evidence is the way stars evolve, they're out there. Okay, galaxies. We talked about our galaxy, the Milky Way, but as we move out, let's categorize what other galaxies look like out there. They come in these different types: spiral, barred spiral, elliptical, which are really kind of boring actually, different sizes and shapes. In addition to that, you have interacting galaxies, because at this scale, the force that's at play in the universe is gravity. So when these galaxies come close to each other, their mutual gravity pulls these tides on each other and distorts them into these interesting shapes. But because there's so much space between the stars, they still pretty much pass through each other. The stars are not going to collide head on like that. They're just going to, swing around each other. But they make for some beautiful views. In addition to the big galaxies we were talking about, there are dwarf galaxies. So if you ever get a chance to travel to the southern hemisphere, there are two dwarf galaxies that are visible called the Magellanic Clouds. And here they are from a trip that I took with my wife down to the southern tip of Argentina and Patagonia. It's really cool to see them. If you don't know what you're looking at, it just looks like a little piece of the Milky Way that got detached. But through a telescope, they show up to be, of course, hundreds of thousands of stars, and then associated nebula star clusters inside, just like a regular galaxy, but just smaller. All righty, now if we zoom out some more, we're going to get to the local group. The bottom right here is our Milky Way galaxy with its assortment of dwarf galaxies around it, including the Magellanic Clouds, of course. And if we zoom out 2.5 million light years, we get to the Andromeda galaxy and its associated dwarf galaxies. 2,730,000 light years away, we get to the Triangulum galaxy, M33. Both of these you can see on a clear night with binoculars or, of course, a telescope. And they are part of our local group. We are gravitationally associated with these guys. The word is that Andromeda and the Milky Way are going to collide or come very close eventually. So we're approaching each other, but don't worry, we're not going to bounce off of each other. We'll just pass through. But this just gives you a picture of what space looks like on a scale of maybe 2 to 3 million light years. Okay, let's zoom out some more. Galaxies form into clusters. And this is the famous Virgo cluster, which is a wonderful target for amateur telescopes. It's gorgeous to look at, and it's something you're going to see a lot of pictures in the Astronomy Club website coming up this spring, because that's when Virgo is up. So people refer to spring not only as migration season for wildlife, but as galaxy season. So the galaxies in Virgo form these beautiful chains, and you can see them with your eye, and they're wonderful photography targets. Here's what the Virgo supercluster looks like. So our local group is just a little bitty part of that, and then the Virgo supercluster groups into these other clusters and clumps of galaxies. And notice that where the galaxies clump together, there are also these big empty pieces, these giant voids around the galaxy superclusters. If we zoom out even more, now we're looking at 520 million light years distance. And we're looking at the Laniakea supercluster, which is just one of many superclusters. You notice again how galaxies form in these giant clumps. Here's a local group. The Virgo supercluster is just a tiny little piece here. And we've got the galaxies and these giant voids. So that's what the universe seems to look like on a very, very large scale. We have sheets, filaments, and voids where the galaxies are all structured together. And then in between the giant voids, just nothing, just incredible emptiness. All right, one of my favorite stories, when the Hubble Space Telescope first went up, they did a little side project. And the idea was to point it at an area of sky where there were no stars. And so in between observing runs, they'd have a few minutes, they'd point it at this empty part of sky that's about a tenth the size of the full moon. And they got, I don't know, something like 100 hours of imaging done to look at this blank part of the sky. The James Webb Space Telescope went back, did the same thing, and showed it even better, because when you look at this empty sky, here's what it looks like. Everything in here is a galaxy except for what's got the spikes. There's something like 2,500 objects out here. And there's no reason to think that this particular part of the universe is specifically, particularly unusually dense. This is what the universe looks like at a very, very large scale. It's just galaxies on top of galaxies. And remember, each one of those, we're talking hundreds of billions of stars. Each star has multiple planets, all separated in time and space by light. And the distances are just unimaginable. So when we talk about looking out any further, we wind up hitting a wall. And the wall is based on the age of the universe. From one side to the other, 93 billion light years, a diameter of the universe, we can't see beyond it, because the universe has a finite age and the light beyond that has not yet had a chance to reach us. So there is a limit of where we can see, and beyond that, we don't know. When people talk about how many galaxies are there in the universe, we can't see past that. There's no reason to think it doesn't go on and on and on. But how far? Does it have a shape? We don't know. We are limited by the light travel time for the age of the universe. So how do we think about all this? Let me just wrap this up. I'm going to tell you one last story. Back in 1990, Voyager 1 spacecraft passed Neptune, its final target to photograph, 4 billion miles out. They're about to turn off the cameras, and because who needs them? There's nothing left to photograph. But Carl Sagan said, wait a minute, let's stop. We have an opportunity that's never been done before. Let's take one last parting picture back of planet Earth from 4 billion miles away. And this was, of course, the famous pale blue dot image that you might have heard of. And Sagan always had a wonderful way of putting into words how we should think about our place in the universe. And I just wanted to close up and read to you a quote from Sagan. It's been said that astronomy is a humbling and character-building experience, that there is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Thanks for your attention, folks. I appreciate it. I'll leave you with this one last slide for some places to go for additional information for astronomy, and I hope you enjoy them as much as I do.
Hey, Rich, thank you very much. Very elegant. You took us from the moon out to the far reaches of the galaxy, and you didn't miss a clip, and you made it clear. So that was wonderful. Really
Thank you,
appreciate
Chris.
that. And I'm going to ask a couple of questions just to kind of get the pump primed here. I didn't see any in the chat. Um, but you had mentioned that the Oort cloud, there was some question about whether or not it exists. That's so I'd like you to kind of maybe expand on that a little bit. And then the second question had to do with Sagittarius A. It's not a stellar mass black hole, I don't think. At least
No,
that's the impression I got. But how the heck did it get here?
well, those are all really great questions. Back on, see, tell me again what the first question was about.
The Oort cloud.
Oracle, yeah, I was kind of surprised that, I mean, the sources that I looked up, they said it's theoretical. And I think what's going on is when they look at these long period comets and they trace the orbit back, they all kind of go back to this area um, around the sun that's way, way out there. There is a limit to how far out they could be because once you get away from the sun at a certain distance, the gravity's going to be so weak, you're just going to break away and go float through the Milky Way. So my understanding is it's the path of these long period comets that suggests that they are representatives of the Oort cloud, and maybe something happened. A couple of them interacted, uh, banged into each other. One of them lost some energy, and then just starts to drop into a different orbit where it comes close to the sun, and we get a great show.
We haven't had any visual confirmation like, say, we would with the asteroid belt.
Yeah, I think the things are just too small.
It's too faint and too far out for us
Yeah.
to catch visually.
Right. And I'm
Yep.
sorry if I gave the wrong impression about Sagittarius A star. There's two things I was trying to cover. Sagittarius A star is huge. It's 4.3 million solar masses, which is typical. I mean, they've imaged another black hole in M87, which I forget how big it was, but it was many, many million solar masses. So
Hmm.
the thinking is that most large galaxies have got black holes at their center. But in addition to the giant supermassive black holes, there should also be smaller black holes. There's a limit, and once a star gets beyond a certain size, when it goes to the end of its life, it's so heavy that nothing can resist the collapse, and it will just keep getting smaller and smaller and smaller until it's gone.
But that's the supermassive black holes. Are they mergers of stellar mass black holes, or
Yes, well,
did
yeah,
they get
probably
here
they're
from
mergers
the,
of something, but I mean, the question is like, well, did these things come from the beginning of the universe? I
okay,
mean,
like the Big
Big Bang,
Bang?
did they originate there?
Okay.
Or did the stars form the Milky Way first, and then at the center there was enough collisions that we started to have some real um, uh, merging stars, and that turned into black holes, and then that brought in more stars, and they just started to run away.
Gotcha.
That's why you need to listen to Neil deGrasse Tyson when he does Star Talk every week. He has some great speakers on that go into this kind of material in great detail.
Excellent. Thank you, Rich. We do have a question in the chat. Let me go back up and make sure I didn't miss anybody. Um, but Victor Venturini, he says, can you comment on the parallel universe that apparently exists on the other side of a black hole?
Yeah, I don't know that anybody really knows for sure what's on the other side of a black hole. I mean, people have speculated that there might be white holes that the black hole might be like a puncture in space and you could go through it and come out the other side. But a lot of that is just mathematical speculation. Nobody's ever seen a white hole, a
Mhm.
reverse black hole. Um, so as far as we know, when things go into the black hole, they just disappear. And now, we discovered that black holes evaporate, they get smaller and smaller over time, they have a temperature. I mean, but what's amazing about black holes is when I was studying astronomy, uh, nobody talked about black holes serious because they didn't really have enough evidence. I mean, Stephen Hawking famously had a bet with Kip Thorne about whether or not black holes exist. And eventually, I guess it was like 10, 15 years ago, enough evidence collected that they decided for sure, the community decided that yes, black holes for sure exist. And I think, I forget who between Kip and I'm not sure who won the bet, but it's been an accepted item in astronomy that black holes for sure are out there.
Gotcha. Nia asks, is there a recording of this interesting and valuable lecture? Yes, there is, Nia, and we will post that on our YouTube channel after the meeting. Let's see. We have, let me get Trent Barber. He asks, can you explain what a standard candle is? As someone just getting into astronomy, I've heard the term a lot.
Yeah, so in astronomy, one of the questions is how do you tell how far away something gets? When you look at the Milky Way or these other things, you have no sense of depth. I was telling my wife the other day, if you've ever been to the Grand Canyon, you look at it, you just go, I got nothing. I mean, once you look beyond what's nearby, the trees and the rocks and stuff, that distance view is just beyond your comprehension. So when we try to figure out how far away something is, like the Andromeda galaxy, how do you do that? Well, they were able to determine something they called a standard candle. They were able to find a class of star that they knew intrinsically how bright it was. And once you know how bright it is, you can measure then how bright it appears to be. And then based on the relationship, how light drops off with distance, you can then infer the distance to the Andromeda galaxy. And that's only about 100 years ago that was done. In the early part of the 20th century, people weren't sure that the Andromeda galaxy wasn't just some big fuzzy extension of the Milky Way. And once they were able to spot individual stars in Andromeda, measure their brightness, and calculate the distance to the Andromeda galaxy, they realized, oh, it's not 1,000 light years away, it's 2.5 million light years away. And if that's an external galaxy, then all the other little fuzzy spiral things must be external galaxies as well.
So one other thing I'll mention, Trent, Bill Spizzeri, who's on our call, actually did a wonderful presentation for the Novice Club on measuring on the cosmic ladder and measuring distances. That recording is still on our YouTube channel, and that actually dealt very deeply with your question. Bill, I don't know if you have any comments to add here or not, but feel free.
Hi, Chris. Yeah, I didn't know the recording was still out there. Thank you. I can just imagine the royalties coming in from that.
Yeah.
But just know if you have an object and you know how bright it really is, and then you look at how bright it looks, as Richard mentioned, you can do the math. You can then tell very accurately how far away it is, and that expanded our knowledge of the universe 100 years ago tremendously. So I would have agree with Richard 100%. But while I'm saying that, I would say, Richard, to say that you covered a lot of information, that is the entire universe in a short period of time, so that we can actually understand all those topics. I salute you. Thank you very much.
Thank you.
Great job.
Thank you.
Awesome. Okay, I'm looking at the chat. Most of the comments here are thank yous to Richard. So well done. If anybody has a question and would like to come off mute at this time, uh, please go ahead and do so. And I've got some announcements that I'm going to wrap up with, so don't leave right away. But if you've got any more questions, come off of mute and ask your question. And I'm going to do my famous auctioneer imitation. So let me see. I had a new comment. Okay. There was a question in the chat from Blanca. She asked, do we have more information about? And Blanca, can you come off mute and ask your question? I'm not sure on the pronunciation of that.
Yes, about I believe it's Umao. It was the asteroid like that. It was an interstellar object, and I don't know if we follow any information or we could have any research that it looks like it was look like more like not like circular or asteroid like. So I don't know if we have anything more.
But it's spelled Oumuamua.
I think it's a Hawaiian name because
Okay.
they found it. So
Okay.
I believe so.
Right. Yeah.
Any information on that, Rich?
Yeah, that was an interstellar comet. Remember, we've there's been three of them. The latest one they've been talking about is Atlas 3I Atlas. So 3I means the third interstellar comet. So what happens is when you see a comet in the sky and you track its position, you can then calculate what the orbit looks like. Well, when they calculated the orbit, it wasn't a closed circle, it was an open hyperbola. And so it came from outside of our solar system, which is really exciting. I mean, here's an object that is not part of our solar system. It's even more exotic than that. And it's come from someplace far away. So Oumuamua, if that's how you pronounce it, was the second one that we've seen. And of course, there was a lot of excitement and speculation that maybe this is some sort of a spacecraft that's come from some other part of the Milky Way galaxy to come check us out. And, I would love that. I mean, I think people get this wrong. Everybody I know in astronomy would love that, but we got to be convinced. And there's been no evidence so far that one or 3I Atlas is anything other than a comet that got kicked out of some other part of the Milky Way, has been traveling for a long time. It's very, very old material. It'd be fascinating if we could get a sample of it, but it's an interstellar comet. Now, what's really cool is the Vera Rubin Observatory has just come online, is able to take pictures of huge chunks of the sky very quickly, and then automatically look at what's there, and it will discover all kinds of asteroids and comets. There are people that have been discovering asteroids, getting their names on them. That era is pretty much come to an end. But I expect it's going to discover a fair amount of comets that are interstellar, because it just takes a close encounter with some large gravitational object, like Jupiter or another star, to kick that thing out of its orbit. And that can very easily send a comet out of its own solar system and out someplace, racing through the Milky Way.
Excellent. Any other questions? Going once, going twice. All right, I think we're done, Rich. Thank you. If you could unshare your screen,
Sure.
I would appreciate that, and then I'll wrap it up here. Um, Very good. And Matt, are you still online? Matt Berlagi? Matt? I guess not. Oh well, that's okay. All
Yes, sir,
right.
I'm having trouble figuring out how to do the unshare.
I think you go down to the little green thing at the bottom of your screen, and I think you can. This will stop. Okay. Did it
Did
go
it do it?
away? Did it go away? Okay.
There you
Can you?
go. There
Yeah.
you go.
Okay. Real good. All right. Good deal. So So Matt, our club president, unfortunately, is not with us anymore. Not, I mean, he's with us, but he's not on the call. But I did have some announcements. So there is a novice lab that we're holding a series of novice labs between November and March. We've got one teed up tomorrow and while I'm thinking about it, I'd like for Cindy, Ricardo and Paul Klein to stay after class. I have to just have a quick discussion with you. Um, but what you would do, or what people have done, I've got a pool of about 15 folks, and I'm trying, whenever the weather's good, we're trying to get people organized to go out to the dark site. And what we do at the Novice Lab is we put into practice the skills that we learn each quarter. So we tour the night sky using the celestial sphere and signposts. We practice finding objects, and then bottom line is we have fun. If you are interested in going on a novice lab, please email me or look at the Discord posts that I have in the novice thread and send me an email. You can send that email to uh, CHRISM at astronomyhouston.org and let me know if you're interested, and I'll put you on the list. Um, and again, it's the weather is kind of a wild card here. There is supposed to be this new thing called Prime Night, and I believe it's a night each month where we go out to the dark side on a Saturday night, kind of an open invitation for those that have passed the dark site quiz, and you can come out. Next weekend, on the 14th, I plan on being out there. So if you even if you haven't contacted me, come on out and I'll be doing my thing. Novice Lab skill set here, and you can participate that way. Matt, I think will send out information on whether or not we're still a go because it's all weather dependent, but that would be on the 14th. And look for information from Matt on that. Um, Special interest groups, and I've got November because it's actually for February, excuse me. Um, but we've already had the data and science SIG. That was last week, or actually this last Wednesday. But we do have the visual SIG, the smart telescope SIG, and the astrophotography SIG coming up each Wednesday this month. And Matt sent out an email with the links to join those. And if you'd like to, please do. And then finally, tomorrow night's meeting is entitled The Nature and Weirdness of the Orion Nebula by uh, Justin McCollum. Uh, this will be an in-person meeting as well. I think you can also join virtually. The details on the location are on the website, so I would encourage you to take a look at that. And with that, I'm going to stop sharing and I'm going to excuse the class.